So the question is, what is sustainability? Sustainability basically brings the three basic elements of it together: the economy, society, and environment. So it could work harmonically. The economy, society, and environment. So here is the framework for strategic sustainable development. It has to identify the important principles that could guide us toward more sustainable path, because the path we are on right now is not necessarily good. It provides a comprehensive definition of an environmentally sustainable society, and it offers a flexible framework for individuals or families, the businesses, communities to create and implement their own plans which will enable them to become more sustainable one step at a time. This is written so well, so I just read it up. But it's important that we actually talk about it and learn about it. So Earth is like a terrarium, you have to imagine. It is a closed system. We're going to talk about that in just a little bit. And Sun is the one who pays the bills. And there is no way. So it means that we have to maintain the balance. It's very, very important because it's like a terrarium. We're going to see if there is any other place outside of the Earth to be able to go to. So in a sustainable society, nature is not subject to systematically increasing the concentrations of substances extracted from the earth crust, like during minings and when we extract oil or coal. What does it do while it's outside? The concentrations of substances produced by society. Just think about the plastic, all the medication in the water, and a lot of other chemicals we produce. Degradation by physical means. And in that society, people are not subject to conditions that systematically undermine their capacity to meet their need. So these are very important things. So let's see if there is any other place we can actually live in the solar system, because I don't think like outside of the solar system it's feasible to go right yet. So this here is showing the solar system, the planets. And I kind of want you to know them in order from the sun. So we're going to talk about the solar system now. You have to understand that all bodies in the solar system were created at the same time from the same general material about 4.6 billion years ago. The same general material basically was hydrogen and helium. The center of the solar system, as you already know, I don't really have to explain this, is the sun. Now, what is important that the sun is a star. The star has a lot of heat in it. So therefore, in the sun, the heat is generated by so-called nuclear fusion. Do you guys know what is nuclear fusion means? Yes, you're right. That's when two particles get together, producing a lot of energy. So in this case, it's two hydrogen atoms fused together to make helium. And during this process, a lot of energy is being formed. So the sun is the largest object in the middle of the solar system. It contains about 98% mass of the whole system. So if you think about all the planets and the sun, 98% of all the material is in the sun. So only 2% is all the planets. The solar energy, as I already kind of told you, that is created deep within the sun, but the hydrogen atoms are fusing together to make helium and creates a lot of energy. And this is only happens when the pressure and the temperature is high enough for nuclear reactions such as fusion to take place. So you understand that we cannot create energy by fusion on Earth because it's kind of impossible to create an environment where the pressure and the temperature is that high. We have done some fusion, but it's very isolated system where the pressure temperature can be increased that high. So this is another picture which shows all the planets, and it has all the low details about them, which you don't have to know. You don't have to know the angle and how long does it take for them to go around the sun and that kind of things. But what you have to know is that the sun's gravitational force is big enough that the planets are orbiting around it, and they are orbiting on the same plane, and that is what you already kind of know, the ecliptic. So the planets are divided into two big groups. One is the inner planets. The inner planets are usually Earth-like. They are more dense and they have rocks. And the outer planets. So let's start with the Mercury. Mercury has almost no atmosphere. So the sky, if you're standing on Mercury and you look up to the sky, it would be black. I think it's very, very depressing. Like you couldn't see basically anything. Mercury has a lot of meteorite craters and long fault system. Okay, of course, it doesn't have any water, and it's pretty small. It's the second smallest planet in the solar system. So what do you think? Is Mercury a place for us? I mean, you cannot breathe, cannot drink. This would be very, very difficult to even try to make it livable. So I think it's a definite no. We cannot live on Mercury. I have more stuff put together for the Mercury. This is interesting information, but I will not ask it on the test or the quiz. But if you're interested in, just go ahead and read it. It's really interesting. Okay, the second one is the Venus. That's the second planet from the sun. We call it the jewel of the sky, and it has very thick swirling clouds. We call it the Earth's sister because it has very similar size, it has similar density, the volume is very similar, and it also has fault systems. However, if we go and look at closer, they are very, very different. There is no water on Earth. The thick atmosphere is composed of CO2, carbon dioxide, which is, do you think it's something we could breathe in? What do we breathe in? What is what we really need when we breathe? Yeah, you're right, it's oxygen. And what do we breathe out? It's mostly CO2. So we would breathe in the stuff which we should breathe out instead of in. So we wouldn't be able to live too long with breathing in CO2. The atmospheric pressure is 92 atmospheres. So it doesn't look very, very promising for us because on the surface of Earth, the atmospheric pressure is 1. So you can imagine if you get up to Venus and the 92 atmosphere would hit you, you'd be dead right away because of the very high pressure. It would just pressure you like that submersible which just got imploded. I mean, it just would crash you right away. And you couldn't even try to breathe the CO2 in because we're already dead. And not even just that, look at the temperature. The temperature on the surface is 482 Celsius. So can you imagine 482 Celsius? If you don't know how to think with Celsius, I'm telling you, in Europe, we cook the chicken at 250 Celsius. So you can imagine that you would be cooked really quickly. How do we change the Celsius from how do we calculate the Celsius into Fahrenheit? So the Fahrenheit is equal to 1.8 times the Celsius plus 32. So you can calculate it over. What I normally do is I multiply it by 2, and it's not right, but it's close enough so you understand. So 482 would be almost 1,000 Fahrenheit. So you know that in Fahrenheit we cook the chicken at 350 to 400 Fahrenheit. So you know that the 1,000 really would burn us quickly. So look at the Venus. CO2 atmosphere we cannot breathe in, has high atmospheric pressure, we would be crashed, and the temperature would be higher than at what we cook the chicken. So we would get crashed, we'd die of the CO2, and we would burn really quickly like a chicken. So Venus is not for us either. So now let's move to Mars. Oh, there is still this side about the interesting part of the Venus, which you can read, but remember, I will not ask it on the test. Oh, and Of course, not the Mars yet. The third planet is the Earth. But look, I only have this really pretty globe here because we're going to spend the whole semester talking about the Earth. So I'm not going to do much about Earth right here. I'm just going to move on to the Mars finally. So the Mars. This is commonly referred as the red planet. The atmosphere is CO2 rich, which doesn't sound so good, but it does have a little bit of oxygen in it, and it doesn't have any moving water present. However, we do have evidence that it used to have water, and the average temperature on Mars is minus 62 degrees Celsius, and we know that it used to have water, and we do know that the water is actually frozen to the poles because Mars is a frozen planet. It is frozen. It froze about 2 billion years ago, about the same time as Earth had the so-called snowball Earth, when Earth almost got frozen all over. And if that would have happened, we would be like Mars, a dead planet. So the average temperature is minus 62 degrees Celsius, so it's pretty cold. But still, if you think about any of the possibilities, probably this would be the best, but of course not like on the surface. You'd have to have a dome in which people could possibly live. And this is the low detail stuff about the Mars. And these are a couple of slides showing the proof of the water presence from the past. Like you can see ripple marks here, like some river activities possibly. So yeah, this is the evidence that there used to be water on Mars. Now we are at the outer or Jovian planets, and these are the Jupiter, Saturn, Uranus, and Neptune. We call them Jovian because that means that they are Jupiter-like. They have gaseous nature, and some of them might have solid core. Other than that, they are absolutely impossible to even think about occupying these planets. Probably some of them has moons, and some of the moons could be Earth-like, which we probably could go to. So now we are going to start turning our focus to Earth. And as you know, Earth is a dynamic planet inside and outside, and it has really well-developed subsystems. The atmosphere, the hydrosphere, biosphere, and the lithosphere. I mentioned the word system, so the question is, what is a system? A system is a group of related things that work together as a whole, like our body. If you think about, we have the kidneys, the livers, like they are all related things and they work together as our body. The nature of the whole is always different from and more than the sum of its unassembled collection of parts. Like our kidney is very different, the purpose and operation is different, but then they work together. So if you think of the system as a whole, it has the surrounding environment, and in between the environment and the system, there is the system boundary. So there is a video here I want you to see, the system approach.
This combining of parts to make something greater than the sum of themselves is what we call synergy. To understand a tree, one expert might study the part of a leaf that traps light, while another might study the chemicals that make plants tilt towards the light, while another specialist might investigate the cells responsible for controlling the movement of essential nutrients. It would be unfair to compare these scientists to the blind men in the parable. For one thing, unlike the blind men who didn't share what they learned with each other, scientists and researchers work very hard to share their findings and build on each other's work, ultimately contributing to our understanding of the system as a whole. If, however, scientists combined all of their collective knowledge on a tree, but never actually saw one as a whole, in its natural environment, could they predict its emergent properties? Can reductionism predict synergy? Maybe, but the systems approach actually observes it. Reductionism explains that studying the individual parts, seeing each jigsaw piece in turn, is all you need to do to see the picture. The systems approach, on the other hand, says, do the puzzle and look at the picture.
So when you think of life on Earth, it could be thought as a complex web of interconnected natural and human-made systems. And our human bodies and brains are individual subsystems within the network of larger biological, economic, and socio-political systems without which we could not exist. So we therefore can be said to spend our lives enmeshed in interdependent living and non-living systems. So what kind of systems do we have? We have closed and open system. A closed system only changes heat. No matter is going to exchange between the system and its environment. Like for example, if you think of your coffee cup, it supposedly changes heat, but no material is coming out unless you drink it. On the other hand, when it's an open system, then it changes material and heat. And most geologic systems are complex, very open systems. So here we are, closed system, only energy goes in and out, no mass transfers. But on the other hand, in open system, you got mass and energy transfer between the surrounding and the system. So we also have to talk about equilibrium. If you think about the natural systems, they do have a tendency to go toward equilibrium, which is the lowermost possible energy level in the system. So equilibrium is the condition in which the net result of the forces acting on the system is zero. So equilibrium is when something is in that condition where the net result of the first forces acting on the system are equal to zero. Now, let's think about the Earth as a planet. It's considered to be a closed system, but inside there is a lot of complicated and interacting subsystems. We already kind of mentioned the atmosphere, the lithosphere, the biosphere, and so on. So here we are. The most dynamic portion of the Earth is the atmosphere. You know, the atmosphere is the thin gaseous envelope which surrounds the Earth. Then you have the hydrosphere, which is a water layer dominated by the oceans. The biosphere is all the living things on the planet. And the last one is the lithosphere, which is the rocky outer shell of the Earth. So here we are. They are absolutely interconnected. They are interacting, very, very dynamic. Lithosphere, biosphere, atmosphere, and hydrosphere. So you should know them all. And in the next part, we're going to go through each of them in detail.